How much of the universe is already dead? You might think the cosmos is in its prime, galaxies spinning, stars blazing across the void. But here's the truth. The universe already peaked billions of years ago. In 1940, a Swedish physicist named Erik Holmberg did something incredible in a darkened gymnasium in Stockholm using 74 light bulbs and photoreceptors. He became the first person to watch millions of years of cosmic history unfold right before his eyes. And what he witnessed changed everything. He saw galaxies stretch, collide, and form breathtaking tidal tails. But he also saw something darker. He watched galaxies die. If you want to discover how much of the universe has already entered its twilight, smash that like button and subscribe, because what comes next will blow your mind. Prepare yourselves. We begin. Picture this. It's 1940, and the world is engulfed in the chaos of the Second World War. Cities burning, nations collapsing. But in a darkened gymnasium in Stockholm, Sweden, a young physicist named Erik Holmberg is about to do something that would forever change how we understand the universe. And he's going to do it with nothing more than light bulbs, photoreceptors, and an idea so brilliant, it would take 30 years for computers to catch up. Holmberg wasn't your typical scientist locked away in some ivory tower crunching equations on a chalkboard. No, this guy was different. He had a vision that was equal parts genius and madness. He wanted to watch galaxies collide, to see cosmic history unfold right before his eyes, to witness events that take millions of years compressed into something he could observe in real time. But how do you simulate something as vast and complex as a galactic merger when the most advanced computers of your era are the size of entire buildings and can barely handle basic arithmetic? Holmberg's answer was beautifully simple, yet incredibly ingenious. He realized that gravity, the force that governs how galaxies interact, follows the inverse square law. That means gravitational force decreases with the square of the distance between two objects. And you know what else follows that exact same law? Light. The intensity of light from a source also decreases with the square of the distance. So if you could somehow use light to represent gravity, you could build a physical model of a galaxy and watch it evolve. And that's exactly what he did. Working with his students in that darkened gymnasium, Holmberg set up 74 stations across the floor, each one equipped with a bright light bulb and a photoreceptor that could measure the intensity of light being received at that location. Each station represented a chunk of a galaxy, an individual piece of mass that could influence its surroundings through gravity and be influenced by it in return. The light bulbs stood in for gravitational force, with their intensity falling off with distance squared, just like real gravity. He divided these 74 stations into two camps, arranging them into the rough shapes of two spiral galaxies, positioned just before a merger event. Think about that for a second. This man literally drew galaxies on a gymnasium floor using light bulbs. Then came the painstaking work. Slowly, methodically, almost like a cosmic choreographer, Holmberg set the lamps in motion. He would measure the amount and direction of light hitting each station, using those measurements to calculate where that station should be placed next, as if that portion of the galaxy had advanced forward about 1 million years in time. After repositioning all 74 stations, based on these calculations, he would repeat the entire process again. Measure the light, calculate the new positions, move the stations, measure again, calculate again, move again, over and over and over. Each iteration representing another million-year leap through cosmic time. Can you imagine the dedication that took? The sheer patience required to manually calculate and reposition 74 points again and again, knowing that each cycle brought you one small step closer to understanding something no human had ever witnessed before. Holmberg had essentially created the world's first analog computer designed to simulate the cosmos, and what he saw in that shadowy gymnasium was nothing short of extraordinary. As the galaxies drew closer together in his simulation, he witnessed exquisite beauty unfold. The galaxies began to stretch and deform under each other's gravitational influence, their neat spiral structures warping and twisting. Long, graceful streamers of matter began to arc outward from the main bodies of the galaxies, what astronomers now call tidal tails, spectacular bridges of stars and gas connecting the two colliding systems like cosmic tentacles reaching across the void. These tidal tails were unlike anything most astronomers of that era had imagined. They swept across hundreds of thousands of light years, monuments to the incredible forces at play during galactic encounters. Holmberg watched as matter from one galaxy was stripped away by the other. Streams of stars pulled from their homes and flung into intergalactic space. He saw spiral arms emerge and dissolve, saw the neat, orderly rotation of the galaxies transform into chaotic tumbling as angular momentum transferred between them. He observed how the cores of the galaxies spiraled inward toward each other, drawn together by their mutual gravitational attraction, moving slowly at first but accelerating as they drew closer, until finally, inevitably, they merged into a single larger system. The dance was mesmerizing, a cosmic ballet played out in light and shadow on a gymnasium floor. But Holmberg saw something else too, something darker and more profound. In the aftermath of the merger, in the patterns of light bulbs and photoreceptors carefully arranged on that floor, he witnessed how galaxies die. The merged system that emerged from the collision wasn't the same as the two spiral galaxies that went into it. The neat disk structure was gone, replaced by something more spherical and chaotic. The orderly rotation had been disrupted, replaced by random motions of stars in all directions. And most importantly, the conditions that allowed for vigorous star formation in those spiral disks had been destroyed. Holmberg had witnessed the transformation of living, star-forming spiral galaxies into something more sedate and quiescent, something that resembled what we now call an elliptical galaxy. He had seen galactic death. The implications were staggering. If galaxies could merge and transform like this, then the universe wasn't the static, unchanging place that many still believed it to be. The cosmos had a history, a story of evolution and change. Galaxies were born, they lived, they interacted with each other, and eventually they died. And by the harsh laws of cosmic expansion that Edwin Hubble had only recently discovered, this process was irreversible. The universe was moving in one direction, from a state of high star formation and galactic activity towards something quieter and darker. There had been a time billions of years ago when the universe was plunged into total darkness before the first stars ignited, and Holmberg realized that there would come a time in the distant future when the cosmos would return to that darkness. In his shadow-filled gymnasium, watching the light from those 74 bulbs flicker and move, Holmberg had witnessed that impermanence. He had seen the future written in the present. But here's what makes Holmberg's achievement even more remarkable. He was right. Decades later, when digital computers finally became powerful enough to run sophisticated in-body simulations of galactic mergers, they confirmed everything Holmberg had seen. The tidal tails formed in the same graceful arcs. The spiral arms emerged and dissolved in the same patterns. The merger timescales matched his predictions. The transformation from spiral to elliptical galaxies followed the path he had mapped out with light bulbs on a gymnasium floor. His analog computer, as crude as it might seem by modern standards, had captured the essential physics of galactic interactions with stunning accuracy. Today, astronomers use supercomputers with hundreds of thousands of cores working in parallel to simulate these same processes, tracking billions of particles instead of Holmberg's 74 stations. But the fundamental insights remain the same. Galaxies merge, galaxies transform, galaxies die. And yet, despite his groundbreaking work, Holmberg's name is largely unknown today, even among professional astrophysicists. His paper, published in 1941 in the midst of World War II, didn't get the attention it deserved. The scientific community was scattered, focused on more immediate concerns, and the implications of his work wouldn't be fully appreciated until decades later, when the space age brought us telescopes powerful enough to actually observe these galactic collisions happening in deep space. But make no mistake, Erik Holmberg, working alone in a darkened gymnasium with nothing but light bulbs and determination, became the first human being to watch millions of years of cosmic history unfold. He pioneered the field of numerical simulations in astronomy. He showed us that galaxies aren't eternal, unchanging objects, but dynamic systems with life cycles of their own. And most importantly, he revealed that the universe we see around us today, filled with vibrant galaxies arranged in a grand cosmic web, will not last forever. The forces that give rise to galaxies also contain the seeds of their destruction. What Holmberg couldn't see, what he couldn't know without the more advanced tools that would come later, was just how far along this process of cosmic death already was. He had glimpsed the mechanisms of galactic mortality, but he hadn't yet realized that the wider universe was already well on its way to oblivion, already past its peak. That revelation would have to wait for future generations of astronomers, armed with radio telescopes, space observatories, and the powerful computers that would eventually replace his light bulb galaxies. But the foundation had been laid. In that gymnasium in Stockholm, in the depths of the Second World War, Erik Holmberg had opened a window into the life and death of the cosmos itself. Look up at the moon tonight, that pale luminous disk hanging in the darkness, and you might think it's been there forever, unchanging and eternal. But here's something that'll mess with your mind. The moon is slowly abandoning us. Every single year, our celestial companion drifts away from Earth at a rate of about 1 inch, creeping away like a guest who's overstayed their welcome and is trying to sneak out without saying goodbye. We know this thanks to something called lunar laser ranging, a technique where scientists blast laser pulses at the moon and measure how long they take to bounce back, with the accuracy of these measurements dramatically improved by optical receptors that the Apollo astronauts placed on the lunar surface back in the late 1960s and early 1970s. Those mirrors are still up there, still reflecting our laser beams, still telling us that the moon is slowly receding into the cosmic distance. Scientists have calculated that at this glacial pace, the moon would only finish its journey and break free from Earth's gravitational embrace in roughly 15 billion years. Except that won't actually happen, because by then the sun will have swollen into a red giant and consumed our planet entirely, turning Earth into nothing more than a charred memory swirling in the outer layers of a dying star. But here's why this matters. If you could rewind time and travel back 4.5 billion years to the newly formed Earth, you'd find yourself standing on a literal hellscape with an earth-shaking rumble permanently echoing across the young globe as the very crust itself shifted and cracked, with molten rock spurting and oozing over a constantly shifting landscape and surface temperatures reaching 1,000 degrees Celsius, or about 1,800 degrees Fahrenheit, with an atmosphere that was almost non-existent and barely different in its makeup from the inside of a solar nebula. And in the sky above this molten chaos would be the moon, but not the moon we know and love. This ancient lunar companion would appear 15 times as large as we see it today, glowing a dull, ominous red and filling the horizon like a dreadful portent of doom. That's how much things have changed. Our night sky is far from static, and on cosmic scales, our retreating moon is just a tiny, almost insignificant example of the relentless transformation that permeates every corner of the universe. Indeed, our entire cosmos is full of change at scales both great and small. From the quantum fluctuations that bubble in the vacuum of space to the grand dance of galaxy clusters across billions of light years, the astronomers of the Renaissance were absolutely astonished to discover that the heavens were just as tumultuous and chaotic as our lives here on Earth, shattering the ancient belief in the perfection and permanence of the celestial realm. Once they realized that Earth itself moved, spinning on its axis and orbiting the sun, rather than sitting fixed at the center of creation, the entire idea of a permanent, fixed, and unchanging cosmos crumbled like a sandcastle before the tide. Comets were discovered not to be strange atmospheric phenomena or omens sent by the gods, but temporary visitors from the outer solar system, icy wanderers following elliptical orbits that brought them screaming past the sun before flinging them back into the frozen darkness beyond Neptune. The bright guest stars that flickered and flared in the night sky, appearing suddenly where no star had been before, and then fading away over weeks or months, were really the deaths of massive suns, supernova explosions that could briefly outshine entire galaxies. The nebulae, those fuzzy patches of light that early telescopes revealed scattered across the sky, were not mere clouds of luminous gas, but either the birthplaces of new stars, stellar nurseries where gravity was collecting material and igniting fusion, or the cemeteries of dead ones, planetary nebulae blown off by dying stars or supernova remnants expanding through space at thousands of kilometers per second. The universe was revealed to be constantly shifting, perpetually in motion, never the same from one moment to the next. And because of that change, because time matters and history has meaning in our cosmos, there are things that have not yet had enough time to be born, and things whose time has passed, phenomena we will never see again, no matter how long we wait or how far we look. To start with, the extremely early universe was radically different from today in ways that seem almost alien to our modern sensibilities. Due to the immense energies present in those first fractions of a second after the Big Bang, the universe may have fashioned exotic particles that no longer exist, strange relics of a hotter, denser, more energetic time. Scientists theorize about magnetic monopoles, hypothetical particles that would carry a single magnetic pole, north or south, rather than the paired north-south magnets we see in nature today. Even stranger are topological defects, like cosmic strings, theoretical one-dimensional tears, in the fabric of space-time itself that might have formed during phase transitions in the early universe, carrying enormous energy densities and potentially stretching across the entire observable cosmos. They're all gone now. If they ever existed at all, vanished into the dustbin of cosmic history, unable to form in the cooler, calmer universe of today. There was a time when the universe itself was capable of creating new elements through nuclear fusion, not in the cores of stars, but everywhere at once, throughout all of space. Primordial hydrogen and helium condensed out of the thick nuclear soup within just a few minutes after the Big Bang, during an era cosmologists call Big Bang nucleosynthesis. For a brief window of time, when the temperature was just right, neither too hot for nuclei to stick together, nor too cool for fusion to occur, the entire universe became one vast fusion reactor. But that window closed quickly as expansion cooled everything down, and it never opened again. Generation after generation of stars have lived and died since then, fusing hydrogen into helium and helium into heavier elements, enriching the cosmos with carbon, nitrogen, oxygen, iron, gold, uranium, all the building blocks of planets and oceans, and the complex molecules that would make life possible. But those heavier elements form only in stars or in the violent explosions that end stellar lives. Except in a few rare cases involving cosmic ray collisions, all the hydrogen the cosmos will ever have was formed in roughly a dozen tumultuous minutes just after the universe began. Think about that. Every hydrogen atom in your body, in the water you drink, in the stars you see, all of it was forged in the first quarter hour of cosmic history. There was a time when the cosmos was so completely unrecognizable that it existed as a totally distinct state of matter unknown anywhere in the modern universe. Roughly 380,000 years after the Big Bang, the universe had cooled to a temperature of just over 10,000 Kelvin, which sounds cool, compared to the trillions of degrees that came before, but was still hot enough to convert all the gas in the universe into a plasma. In this state, electrons weren't bound to atoms, but floated freely, and light couldn't travel more than a short distance before scattering off one of these free electrons. The universe was opaque, filled with a cosmic fog through which nothing could be seen. But as expansion continued and temperatures dropped below 10,000 Kelvin, something remarkable happened. Electrons combined with nuclei to form the first neutral atoms, primarily hydrogen and helium. Suddenly, light could travel freely, and the fog cleared in what cosmologists call the epoch of recombination. The light that was released at that moment, the photons that were freed to travel through space for the first time, is still visible today as the cosmic microwave background, that faint glow of ancient light that comes to us from every direction in the sky, cooled by expansion from visible light down to microwave wavelengths. That one-time event, that cosmic phase transition, will never happen again. The universe can never return to that plasma state, can never experience that clearing of the fog, because it's expanding and cooling, moving in one direction through time. There was a time before stars, a period that cosmologists call the cosmic dark ages, when the only light in the universe was the fading afterglow of the Big Bang itself, gradually red-shifting and cooling as space expanded. There was a time before galaxies, when matter was distributed relatively smoothly throughout space, with only slight density variations, quantum fluctuations, inflated to cosmic scales by the rapid expansion of inflation. There was a time before planets, before the elements needed to build rocky worlds, even existed. There was a time when the first stars poured their light out into the darkness, breaking the cosmic dawn, and these population 3 stars, as astronomers call them, were a supermassive type of sun that seems to have totally vanished in the modern universe, composed of only hydrogen and helium, with no heavier elements, burning hot and dying young in spectacular explosions that seeded space with the first metals. We've never seen a population 3 star directly. They all died billions of years ago, and their time is done. There was an era when the universe was flooded with new stars and chaotic colliding galaxies, when star formation rates were 10 times higher than today, when every cubic megaparsec of space was ablaze with the light of stellar nurseries. That era, which astronomers call cosmic noon, happened roughly 3 billion years after the Big Bang, and it represented the peak of cosmic star formation. Now that time is finished, gone, relegated to history. This story of cosmological change began in earnest with Edwin Hubble's groundbreaking discovery in the late 1920s that the galaxies around us were moving, and in fact most of them were moving in only one direction, away from us. The universe was expanding, and this single observation destroyed forever the idea of a static, eternal cosmos. In a static universe, everything would be the same, no matter where we looked, no matter how deep our observations penetrated into space. We would always see roughly the same things everywhere, the same kinds of galaxies, the same level of activity, the same types of cosmic structures at all distances and all times. But that's not what we found when we started looking deeper into space, which, because light takes time to travel, also means looking backward in time. And Hubble did more than reveal cosmic expansion. He also dramatically increased the known size of the universe almost overnight. Before Hubble's work, many astronomers had believed that the Milky Way was all there was, that our galaxy represented the entire cosmos, and those fuzzy nebulae were just clouds of gas within it. But Hubble's measurements of distant galaxies, particularly his observations of Cepheid variable stars in the Andromeda Nebula, proved that these objects were separate galaxies, millions of light years away. The universe ballooned from a mere 300,000 light years across to a breadth of 280 million light years, almost instantaneously. Over the first half of the 20th century, estimates continued to grow as astronomers developed more powerful telescopes and more effective methods of measuring cosmic distances, reaching over 4 billion light years by 1955. But then came the radio surveys, and everything changed again in ways no one could have predicted. In the late 1950s, astronomers began conducting the first systematic radio surveys of the sky, using newly developed radio telescopes to scan the heavens for sources of electromagnetic radiation at wavelengths far longer than visible light. And what they found blew every previous estimate of the universe's size completely out of the water in a way no one could have predicted. Physicists started detecting strange sources of radio emission, pinpoints of almost impossible intensity that seemed to defy every law of astrophysics they understood. And they dubbed these mysterious objects quasi-stellar objects, or QSOs, because they appeared as point sources like stars, but clearly weren't anything as simple as a star. The name would eventually be shortened to quasars, and they would turn out to be stupendously, almost impossibly bright, compact sources of electromagnetic energy that could outshine 1,000,000 galaxies at once, beacons of such ferocious luminosity that they could be detected across unimaginable distances. But the real discovery, the observation that would forever change our understanding of cosmic history, was that there were no nearby quasars anywhere in our cosmic neighborhood. They were all billions of light years away, existing in a universe that looked radically different from our own. The most distant quasar found in the 1960s was 12 billion light years away, meaning its light had been traveling through space for 12 billion years before reaching our telescopes, showing us the universe as it was 12 billion years ago, when it was less than 2 billion years old. The furthest we've seen in modern times, with advanced space telescopes, is even more extreme, with quasars discovered closer to 13 billion light years distant, existing barely 600 million years after the Big Bang, when the universe was still an infant. And here's the crucial part that shattered the illusion of cosmic permanence. Quasars were primarily creatures of the distant universe, which meant they were only active in the young universe, existing at a time billions of years before the modern epoch. In a static, unchanging universe, we would expect to have some quasars as nearby neighbors, brilliant radio-loud objects scattered throughout our local cosmic environment, just as they are in the distant universe. But we found none. Zero. The nearest quasars are billions of light years away, safely in the distant past where they belong. We could only conclude that the universe was fundamentally different in the past, with conditions that were just right to give rise to quasars, a set of circumstances that no longer exists in the modern era. And this realization led to something even more profound. If the universe was different in the past, actively producing quasars at a tremendous rate, then there must have been a peak, a golden age, when quasar activity reached its maximum, before declining to the relative quiet we see today. This peak occurred roughly 3 to 3.5 billion years after the Big Bang, an era that astronomers now call cosmic noon, the high point of the universe, the moment when everything reached its maximum potential. But quasars weren't the only things that were different in that ancient epoch. Observations of the distant cosmos with the James Webb Space Telescope, that magnificent infrared observatory, launched in late 2021 and now orbiting at the second Lagrange point, reveal a youthful universe inhabited by smaller, dimmer galaxies than the grand spirals and massive ellipticals that populate our local cosmic neighborhood today. The earliest galaxy yet found, with the catchy designation of JDS-GS-Z 14-0, dates from roughly 290 million years after the Big Bang and is absolutely full of new stars being born at a prodigious rate. Although the galaxy itself isn't actually that small compared to some of the dwarf galaxies we see today, measuring roughly the size of the small Magellanic Cloud, one of the satellite galaxies orbiting our Milky Way, which gave it the potential over the intervening 13.5 billion years to grow into a true galactic leviathan through mergers and accretion. Deep cosmic surveys, conducted by both the Hubble Space Telescope and its successor James Webb, find that the cosmic web, that grand arrangement of galaxies on the very largest scales, forming a vast interconnected network of filaments and sheets surrounding enormous voids. It took substantial time to evolve from a diffuse and relatively smooth collection of gas into the intricate latticework that we observe in the modern era. At cosmic noon, galaxies were smaller, more numerous, and far more active than they are today. As galaxies first began to grow in the early universe, the gas pervading all of space fractured and fragmented under the influence of dark matter, collapsing into a series of filaments and sheets rather than remaining uniformly distributed. At the nodes of these filaments, at their points of intersection, where matter accumulated most densely, sat the newly constructed galactic cities, each one a hub of intense activity. Each growing galaxy was attached to the wider universe through numerous umbilical cords of inflowing gas, drawing resources from their surroundings to fuel their growth, and in the process, they produce stars at an absolutely astounding rate that dwarfs anything we see in the modern cosmos. Indeed, at their peak, during cosmic noon, galaxies produce stars at a rate over 10 times greater than they do today, with some particularly active systems creating hundreds or even thousands of new stars every single year, compared to the paltry 7 or so that our Milky Way manages in the current era. If any intelligent creatures lived on the surface of planets in that young universe, orbiting stars in those hyperactive galaxies, they wouldn't need advanced telescopes like the Atacama Large Millimeter Array or the James Webb Space Telescope to witness stellar miracles unfolding around them. They could simply look up at their night sky and be confronted with wonders beyond imagination. Our own sky here on Earth is dominated by the light of only the largest stars, the supergiants and giants that shine bright enough to be seen with the naked eye across tens or hundreds of light years. The stars like our Sun, despite being average in mass and luminosity, are too dim and feeble to be visible over interstellar distances without optical aid, which is why when you look up at night, you're seeing only the most luminous stars in our cosmic neighborhood. But if you could somehow take this same view and transport it back to the era of peak star formation during cosmic noon, maintaining the same eye sensitivity and atmospheric conditions, you would instead see over 30,000 stars scattered across the heavens, perhaps even more depending on exactly where in a galaxy you were located. The entire night sky would be ablaze with stellar light, with hardly any darkness visible between the points of light, creating a spectacular celestial display that would put even the darkest modern sights to shame. This era of cosmic noon represented the peak of the universe's productivity, the moment when everything came together perfectly to create the conditions for maximum star formation. Galaxies were still actively accreting gas from their surroundings through those filamentary streams, drawing in fresh fuel to feed their star-forming engines. The gas itself had been enriched by earlier generations of stars that had lived and died, creating the dust necessary to cool molecular clouds efficiently and allow them to collapse into stellar nurseries. Galaxies were close enough together that interactions and mergers were common, triggering intense bursts of star formation as gravitational perturbations compressed gas clouds beyond their stability limits. And perhaps most importantly, the universe was still young enough that these processes could operate at peak efficiency without being disrupted by the various feedback mechanisms that would later throttle star formation. Japanese astronomer Hideki Umehata used the Atacama Large Millimeter Array, or ALMA for short, situated 5,000 meters above the bone-dry Atacama Desert in northern Chile, to map out one of these cosmic noon wonders in unprecedented detail. He targeted something called the SSA-22 protocluster of galaxies, a monster galactic structure, nestled in a cradle of filamentary matter, nearly 12 billion light-years away, meaning we're seeing it as it existed roughly 12 billion years ago, when the universe was less than 2 billion years old. As galactic wombs go, SSA-22 is absolutely gigantic, reaching over 200 million light-years on a side, containing dozens of young galaxies all forming stars at tremendous rates. Individual gas bubbles carved out by the infant and temperamental galaxies. Within this protocluster measure 400,000 light-years across each. Regions cleared of neutral hydrogen by the intense radiation from newly formed stars, creating enormous cavities in the cosmic gas. ESSA 22 was one of the first such protoclusters of galaxies to emerge on the cosmic scene. And ALMA's observations brought us right into the delivery room, allowing us to witness the birth pangs of what would eventually become a massive galaxy cluster, like the Coma cluster or the Virgo cluster that we observe in our local universe today. This was cosmic noon in all its glory, the universe at its absolute peak of activity and productivity. But here's where the story takes a dark turn. Within a mere 3 billion years after this peak, these same galaxies that were producing stars at such prodigious rates would start to collapse, to slow down, to begin their long decline toward quiescence and eventual death. The very mechanisms that allowed them to grow so large and form stars so efficiently would turn against them, becoming instruments of destruction rather than creation. The umbilical cords feeding them fresh gas would be severed. The dust that helped their molecular clouds collapse would be blown away by stellar winds. The mergers that triggered intense starbursts would ultimately disrupt their orderly structures and heat their gas beyond the point where it could cool and condense. And lurking at the center of each galaxy, growing fat on the same inflowing material that fed the star formation, the supermassive black holes would awaken as quasars, those same brilliant beacons we detected with our radio telescopes, and they would begin to kill their host galaxies from the inside out. Cosmic noon was glorious, spectacular, a time of unprecedented activity when the universe truly lived up to its potential. But it was also brief, lasting only a few billion years before giving way to cosmic afternoon and eventually cosmic evening, the long, slow decline that we find ourselves in today. Star formation continues. Galaxies still merge occasionally, and new stellar systems still ignite in molecular clouds throughout the cosmos. But the pace is far more sedate, the intensity far diminished compared to those heady days of cosmic noon. We are living in the aftermath of the universe's peak, in a cosmos that has already passed its prime and begun its inexorable slide toward darkness and silence. Just as astronomers don't fully understand what led to the great rise in star formation rates during the early universe, they also don't yet completely understand exactly how galaxies die. But observations of dead galaxies combined with sophisticated computer simulations have revealed that it's not usually one single culprit acting alone, but rather a series of events working together to strangle a galaxy of its ability to produce newborn stars. And here's the darkest twist in this cosmic murder mystery. These killers are not any new process or catastrophic event that a galaxy undergoes from outside forces, but the very same mechanisms that gave rise to rapid star formation in the first place, the same processes that built galaxies into magnificent structures in their youth, now turn against them in their maturity and ultimately destroy them. In other words, it seems that galaxies are victims of their own success, betrayed by the forces that created them. The technical term that astronomers use to describe the death of a galaxy is quenching, a word that evokes the extinguishing of fire. And that's precisely what happens as some series of processes snuffs out the flames of star formation, preventing new stellar systems from igniting and relegating the galaxy to join the collection of what astronomers grimly call the red and dead population. There are numerous mechanisms that can participate in this quenching process, and any of them might be more or less important in the evolution of any particular galaxy, depending on its mass, environment, and history. But in the end, all galaxies share the same ultimate fate, regardless of which specific mechanism delivers the killing blow. Sooner or later, some process goes out of control within or around the galaxy and stops star formation permanently. Sometimes, it's just a period of excessively intense star formation that does the trick, which sounds paradoxical, until you understand the feedback mechanisms involved. During these starburst periods, thousands of giant bright stars can appear nearly simultaneously within a relatively small region of a galaxy. And those massive stars, often classified as O-type or B-type stars, with surface temperatures exceeding 20,000 Kelvin, pump out enormous amounts of high-energy particles and radiation, creating stellar winds to accompany their intense ultraviolet starlight. These winds are stronger than any hurricane you could imagine on Earth, but simultaneously so thin that you could pass your hand through them without feeling a thing. Yet when they combine together from thousands of massive stars, all blowing material outward at speeds of thousands of kilometers per second, they can sweep through entire sections of a galaxy, heating up the rest of the interstellar gas to temperatures where it can no longer cool off, condense, and collapse to form new stars. When gas is heated to temperatures of 10,000 Kelvin or higher, the thermal energy of individual particles is too great to allow gravity to pull them together into dense molecular clouds, which means star formation grinds to a halt. Sometimes these stellar winds can be so powerful that they drive material completely out of the galaxy altogether, launching it into intergalactic space, where it can no longer participate in the cycle of star formation, loosened from the gravitational grip of the galaxy, like dandelion seeds carried away by the wind, forever lost to the void. This process of galactic expulsion becomes even more dramatic when supernovae detonate, those catastrophic explosions that mark the deaths of massive stars and can release as much energy in a few seconds as our sun will emit over its entire 10 billion year lifetime. Since clusters of massive stars tend to be born together from the same giant molecular cloud, they have roughly the same age and follow similar evolutionary paths, which means they also tend to die as a group, their lives ending within a few million years of each other. When hundreds or thousands of supernovae explode nearly simultaneously in the same region of a galaxy, they launch massive plumes of superheated material that blow enormous holes in the interstellar medium, cavities that can span hundreds or even thousands of light years. Our own solar system is currently sailing through one such cavity called the local bubble, a region roughly 1,000 light years across that was carved out by a series of supernovae explosions about 10 to 20 million years ago. And we're still living inside this cavity today, surrounded by hot, tenuous gas that's slowly cooling and eventually will recondense. A team of astronomers, led by Artie Camps-Fariña, went searching for these explosive events in nearby galaxies. After weeks of careful observation, they found a spectacular example in MEM 33, the Triangulum galaxy, where they discovered a series of 3 nested bubbles surrounding the galaxy like Russian dolls, each one blown by successive generations of star formation and supernova explosions, with the largest bubble measuring thousands of light years across. Even the very mechanisms that lead to gas accretion onto galaxies can paradoxically contribute to quenching them and preventing further star formation. As galaxies drift through space, they enjoy a steady supply of infalling material that gently rains down from their surrounding environment, mixing with the existing interstellar medium and refilling their reservoirs of star-forming fuel. But galaxies don't move randomly through the universe in isolation. They are gravitationally attracted to each other and pulled toward larger structures, gradually falling into galaxy clusters that can contain 1,000 galaxies or more, all bound together by their mutual gravitational attraction. Threading its way through these clusters is a hot plasma, the intracluster medium, which, despite being thin enough to register as a near-perfect vacuum by Earth laboratory standards, can still play an absolutely critical role in killing galaxies. When a new galaxy enters a cluster for the first time, plunging from the relatively empty space between clusters into this hot, dense environment, it encounters the intracluster medium head-on, and the interaction heats up the gas within the galaxy itself through a combination of compression and friction, raising its temperature and shutting off the formation of new stars. As well as this thermal effect, the simple mechanical process of friction between the gas in the cluster and the gas in the galaxy literally rips material away from the galaxy in a process called ram pressure stripping, named after the ram pressure that occurs when an object moves through a fluid. Astronomers can actually see this violent stripping process affecting galaxies right now in clusters throughout the nearby universe. And when they do, they observe long tentacles of gas streaming behind the galaxies like hair blowing in the wind. And naturally, astronomers have dubbed these unfortunate victims jellyfish galaxies because of their distinctive appearance with trailing tendrils of stripped material. The galaxy is essentially having its atmosphere torn off by its high-speed passage through the cluster environment, losing the raw material needed to build new stars. Once again, the twin effects of heating gas to high temperatures and physically removing it from the galaxy work together to quench star formation, transforming vibrant blue star-forming galaxies into red and dead ellipticals. But there's another killer at work, one that's arguably even more effective than stellar winds or ram pressure stripping or any of the environmental mechanisms we've discussed so far. And this assassin lurks in the shadows, at the very heart of almost every galaxy in the universe. When astronomers look at red and dead galaxies, using radio telescopes, peering through the dust and gas to see what's happening in the core, they often detect long, thin jets of intense radiation, piercing thousands or even tens of thousands of light years through the body of the galaxy. And these jets always point back to the same source, a supermassive black hole squatting in the galactic center like a spider in its web. Supermassive black holes, monsters containing anywhere from millions to billions of times the mass of our sun, appear extraordinarily early in cosmic history, with some detected by the James Webb Space Telescope existing just a few 100 million years after the Big Bang, when the universe was barely 2% of its current age. This means that the story of galaxy evolution has been inextricably linked with the story of black hole evolution from the very beginning, a dark secret that galaxies carry throughout their entire lives, a secret that will ultimately destroy them. For most of a galaxy's existence, the central supermassive black hole remains relatively quiet and inactive, exerting gravitational influence on its surroundings, but not actively consuming large amounts of material or producing significant radiation. While each black hole is individually massive, weighing in at millions or billions of solar masses, they still represent less than 1% of the total mass of their host galaxy, which means their direct gravitational effects are limited to a relatively small region around the galactic center. But everything changes when the black hole awakens and begins actively feeding, transforming into what astronomers call an active galactic nucleus, or AGN, and in the most extreme cases becoming one of those brilliant quasars that first alerted us to the changing nature of the universe. When a clump of matter ventures too close to the central supermassive black hole, whether it's a wandering gas cloud that drifted in from the galaxy's outer regions, or an errant star that found itself on an unlucky orbit, the extreme gravitational field of the black hole tears it to absolute shreds in a process called spaghettification, stretching it into long, thin strands before consuming it. The shredded material doesn't fall directly into the black hole, but instead forms a swirling accretion disk around it, a flat structure of matter spiraling inward like water circling a drain, and the friction within this disk heats the material to absolutely staggering temperatures, reaching millions or even billions of Kelvin. At these extreme temperatures, the accretion disk emits a flood of high-energy radiation across the entire electromagnetic spectrum, from radio waves through visible light all the way up to X-rays and gamma rays. And this radiation doesn't stay confined near the black hole, but rushes outward through the rest of the galaxy at the speed of light. The quasars powered by supermassive black holes don't just heat a small patch of nearby interstellar gas. They can literally inflate an entire galaxy, puffing it up like a cosmic hot air balloon, as the radiation deposits energy throughout the galactic volume. When astronomer Charles Messier published his famous catalogue of deep sky objects in 1781, documenting fuzzy patches of light that might confuse comet hunters like himself. He had absolutely no idea that object number 87 in his list was fundamentally different from almost anything else he'd cataloged. And in fact, he wasn't particularly bothered whether it was different or not, because Messier had only one consuming passion burning in his mind. He really, really loved comets. To quote French astronomer François Arago, describing Messier's obsession, at a time when he was in expectation of discovering a comet, his wife took ill and died. While attending upon her, being withdrawn from his observatory, Montaigne de Limoges anticipated him by discovering the comet. Messier was in despair. A friend visiting him began to offer some consolation, but Messier, thinking only of his lost comet rather than his deceased spouse, exclaimed in anguish, "I had discovered 12. Alas, that I should be robbed of the 13th by Montaigne." Then suddenly remembering that it was socially necessary to mourn for his wife, whose remains were still lying in the house, he added hastily, "Ah, this poor woman," before returning to weeping for his comet. This comet-obsessed astronomer had created his catalog specifically to help clarify which fuzzy objects in the sky were definitely not comets, permanent fixtures that wouldn't fool hunters like himself, and M87 was definitely, absolutely, unquestionably not a comet. M87 was and remains today an elliptical galaxy, and not just any elliptical galaxy, but a true cosmic leviathan containing several trillion stars, making it one of the most massive galaxies in the local universe. Even with modest backyard telescopes, amateur astronomers can tell that M87 looks strikingly different from spiral galaxies like our Milky Way or the famous Andromeda galaxy. There's no flattened disk of stars and gas, no majestic swirl of spiral arms, traced out by young blue stars and glowing nebulae, no obvious structure beyond a smooth, featureless glow that brightens toward the center. This is because M87 is fundamentally different from the Milky Way, different even from most of the galaxies surrounding our own in the local group. M87 is dead, a graveyard of galactic proportions, a tomb containing the remains of trillions of stars that will never be joined by new siblings. Billions of years ago, this galaxy was ablaze with activity, forming new stars every year by the hundreds, or perhaps thousands. Its interior filled with giant molecular clouds collapsing into stellar nurseries, its spiral arms lit up by brilliant O-type and B-type stars, but not anymore. Among astronomers who study galactic evolution, elliptical galaxies, like M87, have earned a grim nickname, the red and dead galaxies. They're called red because the stars that remain are mostly small dim dwarfs, the kind classified as M-type or K-type stars, which glow with a reddish hue and possess only a fraction of the luminosity of our sun, living for trillions of years in some cases, but contributing little light to the cosmic landscape. The massive bright stars that once illuminated these galaxies have all died long ago, exhausting their nuclear fuel within mere millions of years after their birth, and ending their lives in spectacular supernova explosions. And among those still clinging to some feeble form of existence, scattered throughout the dead galaxy, like monuments in a cemetery, are the bones of their ancestors. The black holes, places of such extreme gravity that not even light can escape their pull. The neutron stars with densities so extreme that a teaspoon of their matter would weigh as much as Mount Everest. And the white dwarfs, which are leftover stellar cores that were once capable of nuclear fusion, but now lay dormant as they slowly, almost imperceptibly cool off over billions of years. And finally, drifting obliviously through the darkness, are the planets and asteroids and comets and all the other debris of once magnificent solar systems, orphaned worlds that will never again feel the warmth of a nearby stellar nursery igniting. There are hundreds of billions of red and dead elliptical galaxies, just like Men 87, scattered around the cosmos like rotting corpses, left behind after a great battle, evidence of some catastrophe that struck them down in their prime. Indeed, somewhere between 20 to 30% of all galaxies in the observable universe are ellipticals, and yet, because they can grow to such absolutely massive sizes through repeated mergers and accretion, accumulating the stellar populations of multiple smaller galaxies, roughly 40% of all stars in the entire universe call an elliptical galaxy their home. And here's the terrifying part: their numbers will grow. It's the ultimate fate of every single galaxy in the universe, without exception. Even our own Milky Way, as calm and steady and sedate as it's been for billions of years, with its measured star formation rate and stable spiral structure, will someday become one of these red and dead galactic graveyards. In fact, we know exactly when our galaxy's death will begin, in approximately 4 billion years, when the Milky Way collides with the Andromeda Galaxy in a slow-motion merger that will take another few billion years to complete. And the resulting elliptical galaxy that emerges from this collision will likely undergo a brief final burst of star formation before falling silent forever. But here's what makes this cosmic murder mystery so fascinating and disturbing. Just as astronomers don't fully understand what led to the great rise in star formation rates in the early universe, they also don't completely understand exactly how galaxies die. Though observations of dead galaxies combined with sophisticated computer simulations have revealed that it's usually not one single culprit acting alone. However, there is one killer that stands above all the others in terms of devastating efficiency, one assassin that has been linked again and again to the transformation of living galaxies into dead ones. And this murderer has been hiding in plain sight at the center of nearly every galaxy since the dawn of cosmic time. When we turn radio telescopes toward red and dead galaxies like MEN 87 and peer through the dust and gas to examine their cores, we see something absolutely chilling. A long, thin jet of intense radiation piercing nearly 5,000 light-years through the body of the galaxy, a smoking gun left at the scene of the crime. And when the astronomers of the Event Horizon Telescope, a global network of radio dishes working together to create an Earth-sized virtual telescope, trained their instrument on the center of M87 in April of 2017, they captured something that made headlines around the world: the first direct image of a black hole's shadow. What they photographed was an enormous supermassive black hole, surrounded by a disk of intense radiation, glowing at millions of degrees, with a jet of energetic particles shooting outward at nearly the speed of light, and around it stretched an empty ghost town of a gigantic galaxy devoid of star formation. It looked exactly like the scene of a crime, with the murder weapon still embedded in the victim, and the sinister villain lurking in the shadows at the center. Supermassive black holes, defined as black holes containing more than 1 million times the mass of our Sun, and sometimes reaching billions of solar masses, appear extraordinarily early in cosmic history, according to observations from the James Webb Space Telescope and other advanced instruments. Some have been detected existing just a few 100 million years after the Big Bang, when the universe was barely 500 million years old, and less than 4% of its current age. This means that the story of galaxy evolution has been fundamentally intertwined with the story of supermassive black hole evolution. From the very beginning, a dark partnership that starts innocently enough, but inevitably ends in betrayal and death. Like a parasitic organism that initially helps its host, but eventually consumes it, the supermassive black hole at a galaxy's center begins as a regulator, helping to control star formation and prevent the galaxy from burning through its gas reserves too quickly. But in the end, it becomes an executioner. For most of a galaxy's life, perhaps for billions of years, the central supermassive black hole remains relatively quiet, sitting dormant at the galactic center like a sleeping dragon, while it exerts gravitational influence on nearby stars causing them to orbit at high speeds. And while it may occasionally consume a wandering gas cloud or an unlucky star that ventures too close, it doesn't actively produce significant amounts of radiation or dramatically affect the galaxy as a whole. The black hole is there, massive and dangerous, but contained. However, everything changes dramatically when something happens to wake the dragon, to trigger a feeding frenzy that transforms the black hole from a quiet gravitational anchor into an active galactic nucleus, or AGN, and in the most extreme cases, into one of those brilliant quasars that first revealed the universe's changing nature to 20th century astronomers. This awakening typically occurs after a major merger event, when two galaxies of roughly equal size collide and combine, bringing their central supermassive black holes together in the process. The merger floods the central regions of the newly combined galaxy with enormous amounts of gas and dust, creating a veritable buffet for the black holes. The two supermassive black holes, each having ruled at the center of their respective galaxies, quickly find each other through gravitational attraction and begin a death spiral, orbiting closer and closer while each continues to feed on the surrounding material. Eventually, after millions of years of this orbital decay, they merge into a single, even more massive black hole that settles at the center of the new elliptical galaxy. And then, planted firmly at the heart of this merged system, with access to vast reservoirs of gas, stirred up by the collision, the unified supermassive black hole begins to gorge itself, taking full advantage of this short-lived surplus of available fuel. Once the quasar activates and begins feeding voraciously, it drives so much surrounding gas to such incredibly high temperatures, often reaching tens of millions of Kelvin, that the gas doesn't just resist star formation, but becomes actively hostile to it, heating everything in the galactic volume and preventing any cooling that might allow molecular clouds to collapse. The radiation from the accretion disk is so intense, spanning from radio waves through visible light all the way to X-rays and gamma rays, that it can inflate the entire galaxy, literally puffing it up as the energy deposits throughout its volume, creating a hot bubble that drives material outward. So much gas can be heated and expelled that only a feeble trickle remains available for star formation, nowhere near enough to sustain the hundreds or thousands of stars per year that the galaxy produced during its youth. And if that weren't catastrophic enough, the quasar has one more devastating trick concealed in its arsenal, one final weapon that ensures no galaxy can survive its awakening. The jet, the ferocious energies, swirling in the accretion disk around the supermassive black hole, generate enormously strong magnetic fields, so powerful that they can actually redirect the flow of matter itself, and some of the material that should be falling into the black hole instead follows the twisted paths of these magnetic field lines, getting whipped around the black hole in corkscrew trajectories before being launched outward from the poles of the system at nearly the speed of light. The particles in these jets are accelerated to velocities of 99.9%, the speed of light, or even higher, carrying kinetic energies that boggle the mind, and a cocoon of magnetic fields keeps the jet straight and narrow, preventing it from dispersing as it races outward for tens of thousands or even hundreds of thousands of light years. Any loose material unfortunate enough to be in the path of this cosmic flamethrower is simply shoved out of the galaxy, wholesale, expelled into the intergalactic void, where it can never participate in the grand dance of star formation ever again. And so this was the smoking gun that murdered M87, the evidence left behind at the scene of the crime. Simply too many mergers throughout its history, and a too eager supermassive black hole that grew fat on the resulting influx of material before awakening and destroying its host from within. Though it's worth noting that not all galaxies will die through merger events like M87 did. Some will be lucky or isolated enough, distant enough from their nearest neighbors in the vast cosmic web, that they'll escape that particular fate for billions of years to come. But even if they manage to keep producing stars for eons, by avoiding catastrophic mergers and quasar awakenings, eventually their lights will dim too, because the universe itself is still changing, still expanding, still on average, pulling galaxies away from each other at an accelerating rate. Thanks to the mysterious influence of dark energy, there is only so much material available in the cosmos, only so much hydrogen and helium that can be converted into stars, and eventually, inevitably, all galaxies will simply run out of gas, their fuel reserves depleted, their star-forming clouds consumed, leaving nothing but the slowly fading embers of stars that have already been born. In this sense, galaxies are temporary creations, magnificent but fleeting structures that will live for much longer than the current age of the universe, but still possess only a finite lifespan measured in trillions of years, rather than being truly eternal. And so while cosmic noon, that glorious peak of the universe, when star formation reached its absolute maximum, came and went in what amounts to the blink of a cosmic eye, lasting a mere 3 billion years after the Big Bang, before beginning its decline, cosmic evening and cosmic twilight will last much, much longer, stretching out across hundreds of billions of years. As the universe slowly, inexorably fades, star formation peaked billions of years ago, and we've been on a downward trajectory ever since, living through the long, slow decline of the cosmos. Advanced computer simulations, like illustrious TNG, one of the largest and most sophisticated cosmological simulations ever created by Volker Springel and Lars Hernquist, requiring the use of nearly 100,000 computer cores working in tandem to recreate just a tiny portion of the visible universe, can follow the evolution of gas as it converts into stars and trace the formation of structure across cosmic time. These simulations reveal in stunning detail the hidden mechanisms behind the rise and slow decline of galaxies, showing us flows and processes that observations alone cannot capture. What illustrious TNG and similar simulations demonstrate conclusively is that the universe is well past its peak productivity, that we're living in a fundamentally different era than the galaxies of cosmic noon experienced. The James Webb Space Telescope, that magnificent infrared observatory that launched in late 2021 and has revolutionized our understanding of the early universe, reveals galaxies from the cosmic noon era that are absolutely blazing with star formation, their interiors lit up by thousands of stellar nurseries, their ultraviolet emissions so intense they can be detected across billions of light years. In stark contrast, when we look at galaxies in the modern local universe, we see far more subdued objects, sedate systems where star formation has slowed to a comparative trickle. Our own Milky Way galaxy manages to produce only about 7 new stars per year across its entire expanse of over 100,000 light years. And astronomers actually consider the Milky Way to be relatively active for our current cosmic epoch. That's 7 stars annually in a galaxy containing between 200 billion and 400 billion existing stars, a replacement rate so slow that it takes roughly 30 million years to replace even 1% of the stellar population. In just the most recent confirmation of this cosmic decline, observations from the European Space Agency's Euclid Space Telescope, released in November 2025, have provided the most detailed map yet of star formation across cosmic history, and the data unequivocally confirms that the universe has already passed its peak and entered a period of terminal decline. The Euclid observations tracked star formation rates across billions of years of cosmic time by observing galaxies at different distances and therefore different epochs, essentially creating a timeline of the universe's productivity. What they found was sobering. Star formation rates have been steadily declining for the past 10 billion years, dropping by more than 80% from their peak at cosmic noon. The universe is producing fewer than 20% of the stars per year that it did at its maximum, and this decline shows no signs of stopping or reversing. As one of the astronomers involved in the study bluntly stated, "The universe will just get colder and deader from now on." There's no recovery coming, no second wind that will restore the cosmos to its former glory. We are living through the long fade, the gradual dimming of the cosmic lights. The universe is 13.8 billion years old, having begun with the Big Bang and progressed through the cosmic dark ages, the epoch of regenization, when the first stars ignited, the era of rapid galaxy formation and growth, and the glorious peak of cosmic noon. But we are now roughly 10 billion years past that peak, living in what astronomers increasingly call cosmic evening or cosmic twilight, an era characterized by declining star formation, increasing numbers of dead galaxies, and the gradual exhaustion of the universe's fuel reserves. Much of the universe is already dead in a very real sense. Between 20 to 30% of all galaxies are red and dead, ellipticals that have ceased forming new stars. And even among the spiral galaxies that remain active, many are producing stars at rates far below what they achieved in their youth. If we could somehow tally up all the stellar mass that currently exists in dead galaxies, in stars that will never be joined by new companions, it would represent a staggering fraction of all the stars that have ever formed in cosmic history. Dark energy, that mysterious force that causes the expansion of the universe to accelerate rather than slow down, as gravity would dictate, is effectively starving galaxies by pushing them apart, cutting off the supply lines of intergalactic gas that once fed their growth. The filaments of the cosmic web are being stretched thinner and thinner, the connections between galaxies weakening, the flow of fresh material slowing to a trickle. By some estimates, the universe will stop forming stars altogether within 10 trillion years, though most star formation will have ceased long before then, with the rate dropping to negligible levels within a few 100 billion years. And here's perhaps the most sobering realization of all. By the time Erik Holmberg conducted his groundbreaking experiment in that darkened gymnasium in Stockholm, in 1940, the universe was already well on its way to oblivion, already firmly past its peak. He witnessed the mechanisms of galactic death in his lightbulb simulation. But the wider cosmos was already experiencing those mechanisms on a grand scale throughout billions of galaxies. Every year, more galaxies are quenched, more star formation ceases, more of the universe transitions from living and active to dead and dormant. The process is irreversible, driven by the fundamental physics of cosmic expansion and the feedback mechanisms built into galaxy evolution itself. We often imagine that we're living in a young, vibrant universe full of potential, that the cosmos is in its prime, with billions of years of productivity ahead, but that's simply not true. We are living in the autumn of the universe, watching the leaves fall from the cosmic tree, witnessing the slow but inevitable march toward a cold, dark, empty future, where the last stars have burned out and only black holes and dead stellar remnants remain scattered across an ever-expanding void. The universe is not dying suddenly or catastrophically. There will be no dramatic finale, no cosmic explosion or big crunch that brings everything to a definitive end. Instead, the cosmos is experiencing a long, drawn-out fade, a gradual dimming that has already been underway for billions of years and will continue for trillions more until there is nothing left but darkness and silence, punctuated only by the occasional Hawking radiation from evaporating black holes or the rare flash of two dead stellar cores colliding. So what does this distant future actually look like? This cold, empty cosmos that awaits us at the end of time. The timeline of cosmic decline stretches across such vast expanses of time that our minds can barely comprehend the scales involved, making billions of years seem like mere heartbeats in comparison to the eons that lie ahead. Within the next 100 billion years, something remarkable and terrifying will happen to observers living in galaxies throughout the cosmos. The observable universe will begin to disappear, because space itself is expanding, and that expansion is accelerating due to dark energy. Galaxies that are currently visible to us will be carried away by cosmic expansion until their light can no longer reach us, redshifted beyond detection. vanishing from view as though they had never existed. Any civilization that arises in the far future, say 200 billion years from now, will look out at a night sky containing only the galaxies in their local group, all the billions of other galaxies having receded beyond the cosmic horizon, and they'll have no way of knowing that a vaster universe once existed beyond their isolated island. They'll be cosmologically alone, unable to discover the Big Bang or cosmic expansion, because all the evidence will have literally moved out of reach. But that's just the beginning of the strangeness that awaits in the far future, because as the universe continues to age, new types of stellar objects will emerge that have never existed before, phenomena that require timescales longer than the current age of the universe to develop. Around the 10 trillion to 14 trillion year mark, an entirely new category of stars will make their appearance: blue dwarfs. These are the evolved forms of red dwarf stars. Those small dim stars with masses less than 40% that of our sun, which burn their hydrogen fuel so slowly and efficiently that their lifetimes stretch across trillions of years. In the modern universe, red dwarfs have barely begun their lives. Even the oldest red dwarfs formed shortly after the Big Bang are still in their infancy, having consumed only a tiny fraction of their nuclear fuel. But eventually, after burning for trillions of years, these red dwarfs will have fused enough of their hydrogen into helium that their structure will change. They'll heat up and turn blue rather than cooling and expanding like sun-like stars do, becoming blue dwarfs that shine with a hot blue-white light for a brief period before finally exhausting their fuel and fading to cold, dark stellar corpses. These blue dwarfs will be the final new stars to appear in cosmic history, the last gasp of stellar evolution. Between 10 trillion and 100 trillion years from now, the last star formation will occur as the final reserves of hydrogen gas collapse into stellar nurseries, igniting fusion one last time. After that point, no new stars will ever be born. The universe will have exhausted its raw materials, used up all the gas that could potentially form stars. The existing stars will continue to burn for varying lengths of time, depending on their mass, with the smallest red dwarfs potentially lasting for tens of trillions of years more. But eventually, inevitably, they too will exhaust their fuel. The last star in the universe, likely a small red dwarf in some isolated galaxy, or perhaps a blue dwarf formed from a red dwarf's evolution, will die sometime between 10 trillion and 20 trillion years from now, flickering out and plunging the cosmos into permanent darkness. After that, the stelliferous era, the age when stars illuminate the universe, will be over, replaced by what astronomers grimly call the degenerate era, when the only objects remaining are stellar corpses, white dwarfs, neutron stars, and black holes. But even these remnants won't last forever, because matter itself may be unstable on sufficiently long timescales. If protons decay, as many theories of particle physics predict, though none have yet observed, then all atomic matter in the universe will eventually dissolve, with protons spontaneously breaking down into lighter particles like positrons and photons. The current experimental limits suggest that if protons do decay, their half-life must be greater than 10 to the 34th power years, meaning it would take 10 trillion years for half of the protons in a given sample to decay. On these unimaginable timescales, white dwarfs, those Earth-sized stellar cores, composed primarily of carbon and oxygen, supported against gravitational collapse by electron degeneracy pressure, will slowly evaporate as their constituent protons decay, one by one. Even more exotic objects, composed of neutrons packed together at nuclear densities, with masses exceeding that of our sun compressed into spheres, only 20 kilometers across, will likewise dissolve as their neutrons, which are composed of quarks just like protons, decay into lighter particles by around 10 to the 40th power years. Assuming proton decay occurs, all the white dwarfs and neutron stars in the universe will have evaporated completely, leaving behind only radiation and the black holes that are immune to proton decay. And these black holes will dominate the universe for eons beyond comprehension. But even they are not eternal. Stephen Hawking's theoretical work in the 1970s revealed that black holes aren't completely black, but instead emit a faint thermal radiation due to quantum effects near their event horizons, a process now known as Hawking radiation. This radiation is incredibly feeble, with smaller black holes radiating faster than larger ones, and the temperature of the radiation is inversely proportional to the mass of the black hole, meaning stellar mass black holes in the modern universe have temperatures just a tiny fraction of a degree above absolute zero, far colder than the cosmic microwave background radiation that currently permeates space. But as the universe continues to expand and cool, eventually the temperature of the cosmic microwave background will drop below the temperature of even the largest black holes, and at that point, black holes will begin to evaporate, slowly losing mass through Hawking radiation. A stellar mass black hole of, say, 10 solar masses would take approximately 10 to the 67th power years to evaporate completely through this process, while a supermassive black hole containing 1 billion solar masses, like some of the monsters at the centers of large galaxies, would persist for roughly 10 to the 100th power years, before finally radiating away its last bit of mass in a final burst of energy. By 10 to the 100th power years, every black hole in the universe, from the smallest stellar remnants to the largest supermassive behemoths, will have evaporated completely, leaving behind only a dilute sea of photons and fundamental particles spreading through an ever-expanding space. But the universe's capacity for creating strange phenomena isn't exhausted, even at these incomprehensible timescales, because quantum mechanics introduces another bizarre possibility for the far future: iron stars on timescales beyond 10 to the 1500th power years. Yes, that's 10 to the power of 1500, written as 1 followed by 1500 zeros, a number so large it defies human comprehension. Quantum tunneling could allow the nuclei of atoms to spontaneously undergo fusion reactions, even at temperatures near absolute zero, and calculations suggest that the most stable endpoint of this process would be iron 56, the most stable nucleus in terms of binding energy per nucleon. So any remaining matter in the universe, assuming it hasn't decayed through proton decay, could eventually quantum tunnel its way to becoming spheres of iron held together by gravity, cold dead objects called iron stars that sit at the absolute minimum energy state of matter, objects that would look like black balls of metal drifting through the void, completely dark, completely cold, completely inert. But even these wouldn't be the final state of matter, because quantum mechanics also tells us that on sufficiently long timescales, everything can quantum tunnel into anything else, given enough time. On timescales written as 10 to the power of 10 to the power of 76, numbers so preposterously large that there isn't enough space in the observable universe to write them out in ordinary decimal notation. The iron stars themselves could quantum tunnel into black holes, then evaporate again through Hawking radiation, in an endless cycle driven by the fundamental randomness of quantum mechanics, operating over timescales that make the current age of the universe seem like less than the blink of an eye in comparison. And yet here's the really chilling part. This decay has already begun. We're not waiting for the far future to arrive before the universe starts dying. The process is underway right now, has been underway for billions of years, accelerating from the peak of cosmic noon toward the long dark era that awaits. Every galaxy that gets quenched, every star that forms and dies without being replaced, every supermassive black hole that awakens and sterilizes its host galaxy, all of these are steps on the path toward that ultimate empty universe. The stellar remnants being created today the white dwarfs cooling in the darkness, the neutron stars spinning down and losing rotational energy, the black holes accumulating mass. These are the seeds of the degenerate era, the building blocks of the dead universe that will dominate cosmic history for the vast majority of time's existence. So let's return to where we started, to that darkened gymnasium in Stockholm in 1940, where Erik Holmberg carefully arranged 74 light bulbs and photoreceptors on the floor to simulate the collision of two spiral galaxies, becoming the first human being to witness millions of years of cosmic evolution compressed into observable time. In that shadow-filled space, with the light from his bulbs flickering and moving, as he painstakingly calculated and repositioned each station representing a piece of galactic matter, Holmberg had witnessed something profound and unsettling. He had seen impermanence written into the very fabric of the cosmos. He watched as spiral galaxies, those magnificent structures with their graceful arms and orderly rotation, collided and merged into something completely different, transforming into spherical collections of stars with no ongoing star formation, no bright young stellar populations, no future. He had witnessed how the forces that build galaxies, the gravity that draws matter together, and the angular momentum that spins it into disks, can turn against their own creations and destroy them from within. At the time, Holmberg couldn't have known just how universal this process was, couldn't have realized that his light bulb simulation was showing him not just one possible fate for a few unlucky galaxies, but the ultimate destiny of every galaxy in the entire universe, without exception. Today, 8 decades after Holmberg's pioneering experiment, we have tools he could never have imagined. Space telescopes that can peer back to within a few 100 million years of the Big Bang itself. Supercomputers that can simulate the evolution of billions of particles across cosmic time. Radio telescope arrays spanning entire continents, and theoretical frameworks that connect quantum mechanics to cosmology. With these modern instruments and techniques, astronomers have combined advanced computer simulations with comprehensive observations, spanning billions of light years, to learn something that would have shocked even Holmberg. Despite what he witnessed in his gymnasium, much of the universe is already dead. We are not living at the beginning of cosmic history, not witnessing the dawn of a bright future stretching endlessly before us, but rather existing in the twilight of the cosmos, in the long, slow fade that follows the peak. The universe reached its maximum productivity, its golden age of star formation and galactic activity, roughly 3 to 3.5 billion years after the Big Bang, during an era astronomers now call cosmic noon, and we are currently living approximately 10 billion years past that peak. Between 20 to 30% of all galaxies have already been quenched, transformed into red and dead elliptical systems like M87 that will never form new stars again. And even among the galaxies that remain active, star formation rates have dropped by more than 80% from their peak values. Our own Milky Way, which astronomers consider relatively active for the modern epoch, produces only about 7 new stars per year across its entire expanse of over 100,000 light years. A pathetic trickle compared to the hundreds or thousands of stars per year that galaxies were creating during cosmic noon. In a very real sense, this is a story of betrayal, because in a changing universe where evolution and time matter, the very forces that gave rise to star formation and built magnificent galaxies eventually turned their backs on their own creations and began killing them from the inside out. The stellar winds and supernova explosions that enrich the interstellar medium with heavy elements also heat that medium to temperatures where it can't collapse to form new stars. The mergers that trigger intense bursts of star formation also disrupt galactic structure and ultimately feed the supermassive black holes at galactic centers, causing them to awaken as quasars that sterilize their host galaxies. The accretion of gas from cosmic filaments that fuels galactic growth eventually slows. As expansion stretches, those filaments thinner and dark energy accelerates the universe apart. and perhaps most dramatically, the supermassive black holes that sit at the centers of nearly every galaxy, initially acting as regulators that help control star formation rates, eventually become executioners that murder their hosts by heating and expelling the gas needed for star formation. The jets launched from these black holes at nearly the speed of light, the radiation flooding from their accretion disks, the heating of entire galactic volumes to temperatures of millions of degrees. All of these mechanisms work together to ensure that no galaxy can maintain vigorous star formation indefinitely. And what we face in the long future is nothing but decline, an inexorable slide toward darkness that has already been underway for billions of years and will continue for trillions more. The Euclid Space Telescope's observations, released in November 2025, confirmed what theoretical models had been predicting. The universe is getting colder and deader with each passing year. Star formation rates continue to decline, and there's no recovery coming. Within the next few 100 billion years, most star formation will have ceased entirely as galaxies exhaust their fuel reserves, and dark energy pushes them too far apart to accrete new material. The last stars will form sometime between 10 trillion and 100 trillion years from now, and the last stars will die between 10 trillion and 20 trillion years after that, plunging the universe into permanent darkness. After the stelliferous era ends, the cosmos will enter the degenerate era, dominated by stellar corpses like white dwarfs, neutron stars, and black holes, objects that themselves may decay over timescales measured in 10 to the 40th power years. If protons are unstable, or 10 to the 100th power years, as black holes evaporate through Hawking radiation, on timescales beyond human comprehension, written as numbers with hundreds or thousands of digits, even the stable configurations of matter may quantum tunnel into other states, creating bizarre objects like iron stars or temporary black holes in an eternally evolving, but ultimately dead cosmos. The universe will never experience a dramatic ending. No big crunch, where everything collapses back together. No cosmic explosion or catastrophic finale. Just an endless expansion into cold, empty darkness, punctuated only by increasingly rare and feeble events. And yet here's perhaps the most unsettling realization. We're already living through the beginning of this cosmic death. The processes that will eventually leave the universe cold and dark are operating right now, have been operating for billions of years, and are accelerating. Every galaxy that gets quenched adds to the population of the dead. Every supermassive black hole that awakens as a quasar destroys its host's ability to form stars. Every stellar remnant cooling in the darkness is a step toward the degenerate era. The white dwarfs being formed today from dying sun-like stars will still be cooling off trillions of years from now, when the last stars finally flicker out. The black holes accumulating mass at galactic centers will still be evaporating through Hawking radiation, when the universe is 10 to the 100th power years old, and nothing else remains. We are not waiting for the far future to arrive before the universe begins its death throes. We are living through them right now, witnessing the long twilight of the cosmos in real time. The universe peaked billions of years ago, and everything since has been decline, and everything ahead will be further decline. A one-way journey into darkness from which there is no return. But perhaps there's something oddly comforting in understanding our place in this vast cosmic story, in recognizing that we are living not in the eternal youth or infinite future of the universe, but in its middle age, past the peak, but before the final darkness. Strange wonders will appear in timescales we can barely fathom, phenomena like blue dwarfs and iron stars that require eons far longer than the current age of the universe to develop. The universe may be dying, but it's dying slowly, taking so long to fade that civilizations could rise and fall millions of times over before the last stars burn out. And we are privileged, in a sense, to exist during the stelliferous era, when stars still shine and galaxies still spin, when the cosmic microwave background can still be detected, and the expansion of the universe can still be measured. when the evidence of the Big Bang and the peak of cosmic noon remains within reach of our telescopes. Future civilizations arising trillions of years from now will lack these clues, will be unable to reconstruct the history we've discovered, will live in isolated pockets of dying stars, with no way to know that a vaster, brighter universe once existed. We can look back across 13.8 billion years and see the universe's history laid out before us, can trace the rise from the Big Bang through the cosmic dark ages and reionization to the glory of cosmic noon and beyond, can understand our place in a story that stretches from the first fraction of a second after creation to timescales written as numbers with hundreds of digits. Erik Holmberg, in his darkened gymnasium, with nothing but light bulbs and determination, opened the door to this understanding, showed us that the cosmos has a history and a future, that galaxies are not eternal but temporary phenomena that are born, live, and die. And now, with all our modern tools and knowledge, we've confirmed what he glimpsed in that shadow-filled space. The universe is not infinite in its possibilities, not eternal in its vibrancy, but rather a changing, evolving system that has already passed its peak and begun its long fade to black, a fade that is already well underway.